Good morning, good afternoon, and good evening, everyone. Welcome back. Sorry about this daylight saving time. I have no idea. I'll never understand what's the point of it. Anyways, so if you're watching recording of this, sorry about that. I also completely forgot about this. Anyway, so before I start, I promised Ulam stability today, but first, I just want to go back to lemma 17448, the lemma with stabilizers, just because, basically we wasted first half an hour of last class, and I gave you a rather messy proof. After the class, I realized what I should have said. So I'm going to say that this time at least. So just to remind you what's going on. So we have phi, which is automorphism of Calkin algebra, and assumption. Oh yes, another thing that I was kind of sloppy about. I said just continuous lifting, but I never said continuous in what sense. You see, point here is that theta maps D into the unit ball of B of H. Now on D, we have a compact metric topology, that's clear, but on this space here, on this unit ball, there are several very reasonable topologies. And I was vague. Actually, proof works for any one of them. If you take weak operator topology, strong operator topology, strong star topology, proof works. And also at this point in the proof of the big theorem, we can assure that we have lifting which is as continuous as we want, which is probably clear from that proof. Remember, we were getting continuous lifting by using bare category theorem and that trick with product spaces. And for any second countable space in the range, you can do it. So that's not an issue. But anyways, so I'm really talking about strong topology here. Now, this right proof uses two very simple but very useful lemmas. So the first lemma here is just if you have a projection, then the commutator of that projection and any operator is equal to that on the right-hand side. Now, to prove this lemma, you just need to draw a picture and remember that multiplying by unitary doesn't change the norm. And that's it. And now, once you have that lemma under your belt, you can proceed to prove lemma B, which is exactly what we need. So, and this is the situation that we have in the proof. You have an operator A and B of H and sequence of projection, which is increasing sequence. They're all finite rank projections, and they strongly converge to the unit in B of H. And moreover, if you look at commutators between your operator and these RJs, they're getting smaller and smaller in norm, and you actually have a summable. I mean, the sequence of these norms for commutators is summable. Then this difference between A and this basically conditional expectation of A to a subalgebra, this difference is compact. Lemma B just follows from lemma A by a little bit of induction and just working it out. So this is really what I should have said before starting to prove lemma. And here is what is going on. So basically what you have here is what I said a week ago, or rather a week minus 24 hours ago, given the difference with daylight saving time. Just to remind you, so we are finding recursively this increasing sequence nj of natural numbers, then sj's, which are operators in this product space, which sit exactly between nj's, so we are leaving room in nj's. And they have this property that if you have two elements of this D, okay, all right. So actually there is one modification of the proof that oh no, that's fine. No, this is good. Right, so A and B belong to this, and C and D belong to this later. So basically there is a gap between n of j and n of j plus 1 before you have any two operators, after you have any two operators, And now combining them, mixing and matching them with S of j, which is in the middle. S of j is here. If you change the part which comes before n of j, then norm after doesn't change much, by at most 2 to minus j. And if you change the parts which come after n of j plus 1 and keep this initial segment, then the norm below r of j doesn't change much. And now we just take x to be set of nj's, and s is sum of sj's. Now, the key observation, which I just failed to notice, is that if you fix any x, a little x in this dx, and if you take any j, then the commutator between this difference, theta of x plus s minus theta of x, and rj is at most 2 to minus j plus 2. Now, the fact that this is exactly the sum of these right-hand sides tells you that you just use each one of these ones to prove that. And proof is pretty straightforward. So I'll just leave it to you to work it out. So the point is that exactly these commutators satisfy the assumptions of lemma b. And then you just define theta j to be compression of rj plus 1 minus rj of theta of x plus s minus theta of x. Now this is product type. And by lemma, theta of x is modulo compacts equal to, sorry, I'm saying theta when I mean xi. Xi of x is modulo compacts equal to theta of x plus s minus theta of s. And because theta is the lifting of phi, this is equal modulo compacts to phi star of x, and that completes the proof. So just in case you're wondering what the hell was I doing in last class, basically this part wasn't in the right place. No, sorry. Actually that part is not supposed to be there. This was supposed to be theta of s, not x. Right? Otherwise, I would be getting something else. Right? So this theta of s wasn't there, and because of that, I had to correct my map a few more times and make a complete mess out of that. So this is just the way to go. All right. So if there are no questions, let me just open the chat window. If there are no questions, then let's go to what I promised last time, which is Ulam stability. Okay, so first, as I said last time, Stanislav Ulam basically asked the question for no good reason, just it sounded like a good question, and indeed it is a good question, whether approximate homomorphisms can be obtained only by taking an actual homomorphism which has in the range some sort of metric structure, and then perturbing it a little bit. That is what stability is about. And as I've shown quickly last time, that's not always the case. It depends on the algebraic structure. It also depends on the structure of the metric in many situations. In general, this is a non-trivial question and really well-studied subject. But anyway, so let's just concentrate on what we really need here. Here is what almost immediate motivation, where the almost immediate motivation for us comes from. So it is definition of epsilon representation of a group G in a unital C algebra A. Quite often one takes instead of A to be B of H, because that really, then you do talk about representations of groups. So epsilon representation is a function theta from G into unitary group, such that for any two x, y in G, this difference, which is supposed to be 0, just gives norm at most epsilon. And also, we require that theta of 1 is equal to 1. Otherwise, of course, you could, well, actually, no, we don't have to assume. Actually, this is kind of superfluous. Right. Okay, so that's what epsilon representation is. And here is a theorem which was reproved several times by several people. I'm quite sure at least here is not exhaustive. We just keep on finding more names of people who prove this, maybe with different parameters, different epsilons, slightly different range. But basically, I mean, instead of compact, you can also put amenable group here. And you'll see from the proof exactly why you need something like that. Anyway, the theorem states that if G is a compact group and A is a von Neumann algebra, epsilon is small enough, then whenever you have Borel measurable epsilon representation theta from G to unitary group of A, oh, by the way, when I say Borel measurable, I really mean in ultra-weak topology, for example, which really, again, makes no difference. So from G into U of A, there exists a unitary representation lambda from G into U of A, such that lambda minus theta in norm is at most 2 epsilon. Right, so in this case, one gets quite a good constant. And so what this says is that if you have a compact or amenable group, then the only way to find an epsilon representation of it in some von Neumann algebra is to start from actual representation and just mess it up a little bit. Right, now we don't need literally this theorem. On the next slide, we have a theorem which is what we need, whose statement is somewhat more complicated than this one. So I just basically gave this one as a warm-up. So here is the theorem, which was proved by Berger, Ozawa, and Thompson. I'm not sure, maybe 10 years ago, more than 10 years ago, more than 10 years ago. So assume A and B are unital C-star algebras. A is finite dimensional. Actually, yeah, A is finite dimensional. Epsilon is again small enough. Theta maps, now this is not a typo, maps unit ball of A into 2 ball of B. So I do mean 2 ball of B here. By the way, I see there is a serious lag. I just underlined on my iPad this B2, but underlining did not appear on my screen of my laptop yet. Okay, hopefully it will show up.
It appeared. I saw it when you at the same time that you were talking.
Oh, I see. So it just disappeared. It's still on my iPad, but okay, let me just underline once again to make an experiment to see. Okay, now both of them appear. Okay, so right. So theta is a uniformly bounded Borel measurable function. Actually, uniformly bounded is not necessary because it's a B2, which satisfies that theta maps U of A into U of B. This is useful for some technical reasons, definitely not substantial, as you'll see from the proof. And theta GA is minus theta G theta A is in norm at most epsilon for all G in the unitary group and for all A in the unit ball. And also we assume that theta 1 is equal to 1. Right, so this is approximately multiplicative, but only if one of the factors is a unitary. That's our assumption. In that case, there is uniformly bounded Borel measurable function lambda, again from A1 into B2. Actually, it's going to be, it has to go into well, it almost certainly has to go into B1, but okay, it's not wrong to write B2, which satisfies that lambda minus theta in norm is less or equal than 4 epsilon, and it is multiplicative, so lambda GA minus lambda G lambda A is 0 for every G, which is a unitary, and for every A of norm at most 1. Right, so this is slightly more precise theorem because we have stronger assumption. Right, so theta is not just mapping some group into B, but it actually maps a unit ball of an entire C-star algebra into B. And by the way, really, because A is finite dimensional, this unitary group is compact, so it has hard measure. Right, so the assumption of the previous theorem is satisfied, but the point here is that we actually correct also the image, the behavior of theta on the entire C-star algebra. Okay, so our main goal is to prove Coulomb stability for approximate star homomorphisms, but this is our first and probably the most substantial step in that, and it's a beautiful theorem in its own right. So let's go and prove it. So let me actually, I don't even have to say right Haar measure because you know, A is finite dimensional, so unitary group has Haar measure. And now here I have this name Bochner integral. In case you haven't seen it, it is just Lebesgue integral. Just take definition of Lebesgue integral, and instead of the reals, put any Banach space. So you know, measurable function means measurable with respect to the norm topology on Banach space, and the sums are just defined. I mean, the integral itself, the step functions and everything is defined exactly the way that Lebesgue integral is defined. So it behaves just like Lebesgue integral. And all right, so we define theta prime of A to be this. So it's integral theta of x star, theta of x a d mu of x. So mu is this Haar measure. Now note here, x is a unitary, right? So x ranges over unitaries, which means that this is also unitary. Okay, and clearly this is you know, theta x star, theta x a is supposed to be very close to theta a, but you know, the point is that this is exactly the formula which does the trick, or rather gets us a little bit closer to the proof. So here I just have repeated assumptions of the theorem. So we have that theta sends unitary group into unitary group, and here is the approximate homomorphism assumption. G, oh yes, I should say this. G and X will always stand for unitaries. So whenever I write G or X, it means I have a unitary, and A is something in the unit ball. Okay, so and also we have this assumption that theta sends unit into unit, and here is theta prime, which I just defined. Okay, so the plan is to prove that theta prime is better than theta. It's still not perfect, but it's better, and we'll have some limit at the end of the proof. All right, so as you can see, I wrote these initial equations on the slides just so that you can actually read them, but later on we'll move to writing what's going on. Now, here is one equality. You see, if you look at this integral of theta xg inverse star theta xa, if you do substitution, replace x with xg, and remembering this is a Haar measure, it's invariant under multiplication. What you get here is integral of theta x star theta xga d mu of x, which is exactly theta prime of ga. Okay, and now from there, if you replace a with the identity and g with g inverse, what do you get? Well, on the right hand side, this theta prime of GA is just theta prime of G inverse. What about the left hand side? So this is right hand side. What becomes with left hand side? Well, you have integral theta xg star theta x d mu of x. But now what is that? Well, look, if I look at the left-hand side, if I conjugate it, I get theta of x star, theta of xg, which is exactly this, but with a replaced to g. So what is this? This is theta prime of g, but conjugated. Right, so I can conjugate under the integral sign. This conjugation is a continuous operation. So what we conclude is this here, that theta prime of G inverse is the same as theta prime of G star. Right, so it at least it behaves well in that sense, but it doesn't mean that it's a star it's a homomorphism. We'll have to work for that, but we can still make some estimates here and get what we need to get. Now here is this I here. This is the key expression that we want to estimate this in our proof. So what is I? It's integral of theta x G inverse minus theta x theta G inverse adjoint times theta xa minus theta x theta a d mu of x. Right, so you have a similar expression with A and with G inverse. The first one is conjugated. Now, you see, if you look at theta, this here is in norm less or equal than epsilon by our assumption. And this here is also less or equal than epsilon by our assumption. So from there, you can conclude that I is at most epsilon squared. Okay, but we can also simplify this. I'm not sure if simplify is the right word here, but basically, go through all this and see what is going on. So what is I? Well, we just go. So it is integral theta xg inverse star theta xa d mu of x minus integral theta xg inverse star theta x theta a d mu of x, and there are two more, minus integral of theta g inverse star theta x star theta xa d mu of x, and plus here we have the last one, theta g inverse star theta x star theta x. Okay, so I'm not good at theta of a d mu of x. Now, what is that? Let's look at them one by one. Well, this here, if you take a substitution, x is replaced with xg, this here just becomes theta prime of GA. Right, so the yellow one is theta prime of GA. Then minus, what about the next one? Let's choose the next color for that. What is this? Well, theta of A is a constant. It just goes out. And again, by substitution, x replaced with xg, we get that this is theta prime of G. And we had that theta of A, right? Minus, all right, next color. Okay, probably this one is, I'm not sure. Let's take one which is going to be, oops, this was not highlighter. Let's say this one. So what about this one here? This is G inverse and X and XA. Well, this time theta of G inverse star is a constant. And what we have here is just theta prime of A. So, oops. So it's theta G inverse star and theta prime of A. And now the last one, well, you see the last one is slightly different because here we have theta x star theta x, which is equal to 1. right? So x is a unitary, so we just have integral of constant. So there is nothing really going on there. So we just copy the constant. So it's theta g inverse star theta of a. Okay. Now, what do we have here? Well, okay, I forgot to highlight this one. What do we have here? Well, look. Okay, as you can see, I'm enjoying playing with this highlighter. We have theta prime of A and theta of A, but that's not what I wanted to underline. What I wanted to underline is theta of G inverse star and theta of G inverse star. I can factorize that. And I'll get theta prime of A minus theta of A. Here I have only theta of A. I want to produce what is the missing part. So here is what we have in the next one. I'll just copy the first one, theta prime of GA. And okay, let me just write down this part so that I can remember what comes in the middle. So this is theta G inverse star times theta prime of A minus theta of A. I want theta prime of A, yes. So I have here minus theta prime of G, theta prime of A. When I also add that theta prime of G, theta prime of A, what I get is plus theta prime of G times theta prime of A minus theta of A. I hope this makes sense. So now you can see we can factorize this part here. So what we get is theta prime GA minus theta prime G, theta prime A times, plus theta prime G minus theta G inverse star times theta prime A minus theta of A. Now, why did we do all that? Well, you see, this is what we want to understand, right? This is what we want to estimate. We know that the entire thing has norm at most epsilon squared, but now look at this part here. This here is at most epsilon. Sorry, it's not at most epsilon, it's 0. What? No, it's not 0. Right, yes. So theta prime of G is within epsilon. What did we say? No, I didn't say anything there. Hold on. I want this part here. Let me just. Sorry about this. So this part here is supposed to have norm at most epsilon squared. Wait, did I forget to say something? I think I've skipped. Oh. Okay, right. Right, yes, so. Yeah, okay, so here is what I should have said before I started these computations. That, so here's claim that norm of theta minus theta prime is at most epsilon, right? This is obviously important. And the reason for that is it's basically immediate from the formula. You see what we have is that theta x star theta xa minus theta of a. So this is what we need to estimate. The norm of this because theta of x is a unitary, I can multiply by it on the left without changing norm. So this is theta of xa minus theta of x theta of a, and this is less or equal than epsilon. Right, so this is proof of the claim. Yeah, okay, so as I said, I was never much into epsilons, but I just feel that I should go over this. Right, okay, so once we know that, this part is at most epsilon squared, and therefore, this here, by the triangle inequality, is at most 2 epsilon. Right, so therefore, theta prime xa minus theta prime of x, actually I called it g, but okay, it's the same. This is at most 2 epsilon squared for every x which is a unitary and for every little a in the unit ball. All right, so now what do we have here? Well, we started from function theta, which was our approximate morphism, and we obtained this theta prime, which is within epsilon of theta, and it has a better constant. Right, so if epsilon is small enough, 2 epsilon squared is much smaller than 2 epsilon. And now just the problem is okay, so before the problem, what you want to do is now use theta prime to construct theta double prime, and it will be within 2 epsilon squared of theta prime, and this error here will be 8 epsilon to the 4th, and so on. So basically get a sequence. Now there is just one minor issue that needs to be resolved before one does that. So we don't know the answer to this question. If you take theta prime and say take unitary group of A, is this subset of unitary group of B? Right, because the proof used that very seriously. But now, basically, one can correct that at the expense of increasing the epsilon just a little bit. And this is the point that I made before I started proving this. You see, when we are applying theorem, this theorem, what we are going to have is just some approximate star homomorphism, so which is Borel measurable. We'll just have to first correct it to get it to send unitary group to unitary group and unit to unit, and then we'll be able to apply this theorem. So basically, this correction needs to be done also before the theorem is applied. Now, how do we do that? So the answer is not quite, but almost. Right. So what it means is just to fix some g, and as I said, g is always unitary. Now, what do we know about g? So if we, sorry, my iPad just froze for a moment. No, it's okay. So what we know is that theta prime of g a minus theta prime of g theta prime of a is less or equal than 2 epsilon squared. Now, if I, no, my iPad sometimes refuses to scroll. Now it's okay. So now what we do? Well, we replace a with 1 and replace, no, we don't. We replace a with g inverse and keep g as it is. Right, so this is true for such A's. What do we have on the left-hand side? Well, theta prime of GA, it is 1. And 1 minus theta prime of G, theta prime of G inverse, is less or equal than to epsilon squared. Okay, but I apologize for this inconvenience. If anybody knows why is iPad occasionally refusing to, Okay, so it works with my left thumb, it doesn't work with my right thumb. If anybody has rational explanation, I would love to hear it. Anyway, and it also works with my left index finger. Anyway, so now a while ago, we proved that theta prime of G inverse is equal to theta prime of G star. Now, what that means? Well, it means that norm of 1 minus theta prime of, okay, I wanted the other way around. All right. Okay, it makes no difference. Let me just continue this way. Theta prime of G star, this is less or equal than to epsilon squared. Now, what that means is that you see this operator, theta prime of G, theta prime of G star, it is a positive operator. And because these are unitaries, it's less or equal than 1, but it's greater or equal. Sorry, they're not unitaries. They're not unitaries. Why is this less or equal than 1? Well, because if you look at the definition of theta prime, if you give me a unitary, I'm just integrating unitaries. So the norm, you're integrating function which is everywhere, has norm 1. So norm can only drop below 1. So it's less or equal than 1, but it's greater or equal than 1 minus 2 epsilon squared. Right. So what that means is that the norm of 1 minus this square root of this is at most 1, and in particular it implies that 1 minus theta prime of G absolute value is less or equal than to epsilon squared. Well, it's actually better than that, because this is just by spectral theorem. Basically, you can get a better estimate, but this is not about an estimate, the estimates. So theta prime of G is not too far from epsilon. So we just define theta double prime of G to be theta prime of G times theta prime of G absolute value inverse. This doesn't change things too much because this is close to 1, and theta double prime of A is just theta prime of A if A is not unitary. And then there are a few more estimates. So basically, I don't think there is much point in going into these estimates, in public. And I think Hilbert said never make computations in public. So basically, then one can just check that if you look at double prime, theta double prime GA minus theta double prime G, theta double prime of A, this is in the norm at most 14 epsilon squared. Basically, by just seeing how far theta double prime is from theta prime, and actually that is what needs to be done first. So maybe I should write that. Theta prime double prime minus theta prime. This is less, actually, don't care about theta prime, we care about theta. Less or equal than 2 epsilon, which is kind of lousy estimate, but it's good enough. Okay, so you see what we did. We started from theta, And after integrating and this minor modification, we obtain theta prime, which satisfies the same assumptions with a better constant, with constant 2 epsilon squared, and it is within 2 epsilon of theta. So now define theta triple prime using the same trick. Right now, what we have? We'll have that theta triple prime minus theta is at most 2 times the error of theta double prime, which was 2 epsilon squared, and also theta triple prime will satisfy that theta prime of triple prime of gx minus theta prime triple prime of g theta triple prime. This is A. A is an arbitrary one. Way. This is at most 2 times 2 epsilon squared, which is 8 epsilon to the 4th, and so on. So basically, by doing this, we construct this sequence of functions. Right. So find this theta nth derivative, and then just take limit as n goes to infinity of these theta n's. This converges to function as required, which was supposed to be lambda. Right. So the elements of this proof were present in previous. Basically, proof was slowly crystallizing, but this is really the best. I mean, from Berger, Ozawa, and Thom, probably the simplest presentation. So essentially, once again, the trick was always to somehow integrate and correct the error. Yeah, okay. So that was the first lemma of today. Now what do we have? So we have unital operator algebras A and B, and we have a group homomorphism between their unitary groups. Question is, when can it be extended to a star homomorphism from A into Oh yes, epsilon. Yes, it is. It is. You see, let me right. So as always, Pedro has a good question. Let me see. That there was something here, for example. Okay, it's not used in that form here, but you need to know that this is less than 1. So it's not that, because you want this guy to be invertible, right? So epsilon does have to be small enough. Less than 1/28. Well, you see, actually, I skipped calculations at the end of the proof because they get somewhat messier. So as far as I know, they were used only for these two. Let me just check the proof. Okay. Sorry. No. I lied to you. Thank you. Yes. So this is. Where did I write that? Right. Actually, here. No, I didn't lie. I wrote it. So you see here it's 14 epsilon squared. Okay. So you don't really need less than 1/28, but you definitely want this to be small enough in order to be able to run the argument. Let's see. So you definitely want that to be a bit smaller than epsilon. Now, I'm not sure exactly how I came up with 28. I think that in their paper, it's some other constant. But this number 14 here, Yes, so the answer is probably not. We can probably get away with something better than that, but not that much better. And I basically made no serious effort to find the optimal constants, because for our purposes it only matters that for every epsilon there is a delta, so that every delta approximate homomorphism can be approximated by epsilon approximated by a star homomorphism. But yeah, so I'm not sure. That's a short answer. Right. So back to this. And the fact is that the answer is not always. There are examples. So I'll just give a reference. Day has a rather old paper, classical, in which he studied von Neumann algebras and situation in which homomorphism, just homomorphism without any topological assumptions between unitary groups of von Neumann factors can be extended to a star homomorphism. And there are some interesting counterexamples, but in most situations, the answer is you can do it. But in our situation, it's actually going to be surprisingly tricky to get exactly the theorem that we need. And here is exercise which actually serves as a somewhat misleading hint. Every element of a C-star algebra, so of course you need to assume that C-star algebra is unital, can be written as a linear combination of 4 unitaries. Okay, why is that so? Well, first you can write A as linear combination of 2 self-adjoints, its real and complex part. Now, there is a little trick. Maybe I should say it here. So, so here is basically the key trick. So if A is a positive contraction between 0 and 1, then A is a convex combination of 2 unitaries. All right. And I think I'm going to embarrass myself now by trying to remember what the formula was. Let's try. So U is something like, take A plus I times square root of, I think I want 1 minus something like this. Let's see, is this a unitary? Okay, so okay, so let me just write what there's something like this. So U is that, and V is the conjugate of U, right? So the product of these two, yes, okay, right. So these are both unitaries, and their product is 1, and their convex combination is equal to A. All right. So anyway, this was a silly digression. You see, every element can be written as a linear combination of 4 unitaries. So if you are not thinking very hard, you may say, okay, so it's obvious what our function is. But now the problem is that this is not unique. That unitaries can be written in many ways as combination of 4 unitaries and many other operators. So basically, one has to do something else. And because of that, we need some better criterion. And here is a lemma that we are going to use that goes back to the A. So this was his trick why he was able to work with 2-1 factors and prove that isomorphisms between unitary groups extend to isomorphisms between algebras. So suppose that A and B are unit LCist algebras, and lambda is a group homomorphism between unitary groups. And now another assumption, you need that A has a faithful tracial state tau. Now remember, faithful tracial state means that tau of A star A is equal to 0 if and only if A is equal to 0. Right, so the corresponding GNS Hilbert space is faithful. I mean, A is the kernel is trivial, and B has also faithful tracial state sigma. Although I don't think that you need faithful for B. I'm quite sure that you don't. But anyway, and you see lambda preserves the faithful trace. So if you compose lambda with sigma, you get tau. Right? Then lambda has unique extension to a star homomorphism. Right, so this is definitely not a necessary condition, but it suffices, and that's exactly what we want, because in our situation, you have that A is a matrix algebra and B will be some finite dimensional, actually matrix algebra as well, and they'll both have unique tracial states. And we'll make sure that tracial states are preserved. Okay. All right. So basically, the point of the proof is you know what the map should do, right? But by the exercise, every element of A can be written like this. UJs are unitaries. So we need to check that this obvious map is well defined. All right, so what does this mean? So this means, because these are vector spaces, we just need to check that kernel is in the right place, that this is equal to 0 implies that some j less than n, lambda j, lambda uj is also equal to 0. Right, so if we check this, then even though this is not a unique representation, it will be unique up to adding or subtracting something of this form. But then to the right hand side, you can add or subtract the same thing, and there is no difference. Now, how do we check this? Well, now, what does this mean? This is equivalent. Oops, it's not a good idea to use a highlighter for this. So this is equivalent to saying, because these are operators, that if I take sum lambda j uj star, sum j less than n, lambda j uj, that this is equal to 0. All right, but now we can just multiply this. So what do we have here? So we have, let us see how much do I need to write here. Oh yeah, of course. Hint is in the statement. So you have faithful tracial state, right? Basically, everything was on the slide, but I just forgot to look at the right place. So this is equivalent to saying that tau of that is equal to 0, right? So what is tau of that? So it's sum j less than n and sum I less than n of lambda j conjugate, lambda I, uj star, ui, except I forgot to write tau. So if and only if this is equal to 0. All right, but now we have our assumption, right? That tau of this is the same what we get if we compose lambda with sigma. So it's if and only if sum j less than n, sum I less than n, lambda j, this is j conjugate, lambda I, sigma of capital lambda of uj star ui is equal to 0. And now we just do the entire calculation backwards, right? So this is equivalent to saying that sum over j less than n, lambda j, not uj, but capital lambda of uj is equal to 0. Right, so simple trick, but exactly what we need. All right, so far what we have is that our group homomorphism can be extended to star homomorphism of the entire algebra, but we still have to see that it works, that it is the right star homomorphism, and that actually,
Can you ask you a
yes,
question?
yes, of course.
Where did you use that they were traces and not only any states?
Good point. Good point. Okay, so I don't use it. Okay, I don't know. I'm not sure whether proof of this uses it, but in application, you see, I'll have that both A and B have a unique tracial state. And this unique tracial state will be mapped to unique tracial state. Yeah, but I don't think. No, it's an excellent point. So although this is always stated in terms of tracial states, yeah, but you're right. You're right. It doesn't use it. It's just easier to get hold of tracial state because, you know, especially if it's unique. Right. Yeah. No, it's, as far as I can see, it's not being used. Let me just check. Maybe I just smudged something in the proof, but no, you're right. Right. That's a good point. That's a good point. But I'm quite sure that this goes all the way back today. That he also, but you know, it's always that it's easier to make sure that it goes to the right place if it's unique in some sense. Yeah. All right. So back to our theorem. So you know, at this point, it seems that we should be done, but there are still quite a few tricks that we need. And here is a good one. So this is Marshall Stone. His one-parameter group theorem. Now, this is not the usual statement. Usually, when you say Stone's one-parameter group theorem, you talk about strongly continuous one-parameter group in B of H. What I need is a version where we have norm-continuous one-parameter group. Okay, so let me just state what's the theorem. So you have group homomorphism from R. Now, this is R. R with plus. So the abelian group R with respect to addition. There is a group homomorphism from that into unitary group of B. Here is U sub T. It's norm continuous. Then there is a self-adjoint element of the target algebra such that UT is exponential of ITB for all T. Right, so here we are just using continuous functional calculus or even holomorphic functional calculus. This is just defined as sum of the series, and it's straightforward to check that if you choose any self-adjoint, this will be one parameter norm continuous one parameter group. Just one warning, that's because you just have single self-adjoint. You're just using the format e to x plus y is e to x times e to y, which is actually false unless x and y commute, but that is not an issue here. So anyway, so we'll need this theorem. And here is the definition that I stated last time in terms of motivation for today's class. Let me just read it, although it's more of the same. Given epsilon greater than 0 and C-star algebras A and B, some theta mapping unit ball to unit ball is epsilon star homomorphism if for all x, y in unit ball of A and for all scalars or absolute value at most 1, each one of the obvious expressions, so it's theta x star minus theta x star, the one corresponding to addition here, one corresponding to multiplication, and finally corresponding to multiplication by scalar. So each one of those has norm not greater than epsilon. And we say that theta is unital if in addition it maps unitary group to unitary group and it maps 1 to 1. Now, having seen the proof of the previous theorem, you know why is that convenient. But as I said, at the expense of getting reverse constant, this last assumption is not a big deal. If you just choose sufficiently small epsilon, and if your epsilon star homomorphism is Borel measurable, or as measurable as you want, you can correct it to something that is unital, and which is still epsilon prime homomorphism for certain epsilon prime, which is still small enough. Right. And what we want to prove now is a Coulomb stability of those epsilon homomorphisms, and here it is. So here we again have 1 over 28. It may be that here we'll need that epsilon is small enough. Maybe that's anyway. So this is definitely false if epsilon is too big. And definitely, I paid no attention to attempt to get the optimal constants. Just not because it's not interesting, but just because it just didn't matter at all. Oh yes, actually, before I move on, you see there is a bit of arbitrarity in this definition, and this is not what some people would consider approximate homomorphism. For example, Barry Johnson considered something very similar to this, but from functional analysis point of view, it is much more natural to somehow bound. Okay, first, it's more natural to just assume that map is linear to start with, because it's only natural to consider linear maps. But also, if you want to look at norm of this, it's sometimes more natural to bound it by depending on what is norm of x and norm of y up to some epsilon. So let's say that norm of this is less or equal than epsilon times norm of x, norm of y, instead of just requiring exactly the same precision for the entire unit ball. Now, the point is that this definition was chosen carefully, and this is exactly what we need. Because remember, we are trying to find a lifting which will work on the unit ball. And now for that to work, we need to know that unit ball behaves uniformly, that everything is equally good in unit ball. So, so basically, this is just one of possible multitude of Coulomb stability results for C-star algebras, but it is one that we need. All right, so here. So if epsilon is small enough, m is greater or equal than 1, A is C-star algebra with faithful threshold state, sigma, and I should say A is unital. And theta from m by n matrices into A is unital epsilon star homomorphism. Then there is a star homomorphism phi such that theta minus phi in norm is less or equal than 16 epsilon. Again, I have no idea whether constant is optimal. Now, how does the proof proceed? Well, of course, the first step is obvious. We have a Borel measurable lambda from unitary group into A such that it is multiplicative for all u and v, and lambda minus theta is less or equal than 4 epsilon. All right. Now we need to see where the other elements go. And you see, the fact is that the previous this sort of answers Daniel's question, that the lemma which guarantees that we can extend this map talks about tracial state. So we need to check that lambda does preserve tracial states. Now we have MM definitely has a tracial state, and A just has a faithful tracial state sigma. We don't know anything else about it. What we want to do is prove that lambda sends tracial state on MM to sigma. All right, and for that we need Stone's one-parameter theorem. So how do we use it? Well, you see, if you give me any, let me just explain what's going on here. So if you give me any self-adjoint element, little a in A, then this exp of IRA gives you one parameter, the norm continuous one parameter group inside unitary group of A. Now, because lambda is continuous, oh yes, actually, right. So I was just about to say lambda is continuous. How do I know that? How do I know that? And this is an important trick. So you see, we know that lambda is Borel measurable. Lambda is this limit of this sequence of better and better approximations. Now, A is C algebra, but the range of lambda, since lambda is Borel, I mean, the range of lambda is separable. So I can just take a separable subalgebra of A. And what do I have then? I have lambda, which is Borel measurable homomorphism between unitary group of M by M matrices and unitary group of A. Unitary group of A is separable. It's a Polish group with respect to norm. And there is a beautiful theorem, well, I mean, easy, but beautiful theorem of Pettis, which states that if you have a Borel measurable, or even weaker, homomorphism between Polish groups, it is automatically continuous. So by Pettis theorem, we have that lambda is continuous. All right. So lambda is continuous, which means that if I feed one parameter group into lambda, it is going to pop out another one parameter group. So this one parameter group by Stone's theorem has this seed, this self-adjoint operator, and I called it lambda tilde of A. All right. Now, how do lambda tilde and lambda relate? Their domains are not disjoint, but we still have to figure out how what is going on. Now, here are two immediate facts about lambda tilde with a very similar proof. First one is lambda tilde of 1 is equal to 1. Now, this may seem obvious, but we have to prove it. You see, what is, if you just put 1 here, you just have exp of IR, you just have scalars, you just have a circle group, right? And how do we know that it goes to circle group? Well, so Let's prove it. So let B be lambda tilde of 1. And we go for contradiction. So suppose that there exists, I'm overusing lambda, I hope you're okay with that there exists lambda which belongs to spectrum of B minus 1. Right? So I want to prove that B is equal to 1. B is self-adjoint, so it's spectrum. Actually, I shouldn't be calling it lambda. I guess lambda is for complex number. Let's call it R. So there is something else there. Now, what do we have? Well, lambda. Okay, so just fix T in R such that T times lambda minus 1 is equal to something nasty. I think I want pi, for example. Right? So, okay, T is pi over this. Now what? So what that means is that exp of it lambda tilde of B in its spectrum has a number minus 1, right? E to I pi. However, this here is very close to what was the name of the original map, theta. This was very close to lambda of it, and lambda of it was very close to theta of it. So I'm not sure now. I forgot what are the epsilons, but these are some. I just call them delta and delta prime, right? So they're small enough, but definitely minus. But theta. What? Oh yeah, right. So okay. So this is maybe not the optimal way to do it. This is scalar. Oh, sorry, I have to look this up. Yeah, this is just too easy, so I'm not sure. By the way, I should warn you, in my book, the proof of this theorem is, there are some issues with it, so you should look at the errata page for the actual proof, where it's done properly. Okay, so let me just wave my hand because this is really silly. So basically, if you look at this one parameter group corresponding to the unit, it is just the circle group. If you have something else, even some other scalar, oh, silly me, of course. Right, right, this is R. You see, I shouldn't have written lambda. This is R. R is a real number. So if you have any real number other than okay, I know that I'm missing something silly. I just forgot what it was. Yeah. Oh yeah. Okay. Right. Yeah. So you see, if t times r minus 1 is equal to pi, yeah, okay, so this is high school math, I guess, but it means that if you look at I e to I tr and e to it, these two are quite far from one another, right? So the distance between them is 2, I think, right? So if you divide by IE to IT, you get, yeah, right. So what that means is that if you look at theta IT, it is one scalar, but theta, not theta, yeah. So theta IT is one scalar, but IT is a completely different scalar. So you have that this map, which is supposed to be approximate homomorphism, basically makes a mistake even at something like this. So I know this is not a proof, but it should follow. Yeah, you know what? I'll just come back to this next time. For now, let me just say that proof of part 2 is very similar also. So basically, you also assume that this is not a projection, It is self-adjoint, so it's in spectrum. It has something that is neither 0 nor 1, and then you just multiply by scalar magnify the difference, and somehow get a contradiction out of that.
Sorry, can I ask
Yes.
a question?
Yes, of course.
When you wrote the spectrum, you have a gamma tilde, sorry, lambda tilde b.
Yes.
Why can you evaluate that at b? Because isn't b in the right side, or am I confused?
Wait, b is lambda tilde of 1.
Yeah,
so
then
b is self-adjoint, right?
But 2 lines down, you have.
Oh, you mean here? Sorry. What I meant was b. Yes, thanks. Yeah, this is what you meant, right?
Yeah.
Yeah, sure. Thanks. Thank you. Of course. This is what I should have written. Yeah.
Thank you.
Yeah. Thank you. Right. Yeah. All right. Okay. So here is just a reminder of what we are doing. So we have this theta, which is epsilon star homomorphism, and we have group homomorphism, which is within 4 epsilon of our theta, and we have this lambda tilde, which have self-adjoint to self-adjoints, and here is the property of lambda tilde. And now here is the key claim. If we have projections P and Q, then actually, if we just have one projection for now, lambda tilde of P is 1/2 1 minus lambda of UP. UP is 1 minus 2P. So you see, this is a unitary, which is also a self-adjoint. If P is a projection, this is a unitary. Now, for this, you just basically look at definition. If what is lambda tilde of P. Let me. Maybe it's a good idea to rewrite UP. So what this is really. Just a second. So it's 1 minus P, okay, times e to 0 plus P times e to IP. This may look silly, but it shows what the spectrum is and what is happening there. So if you just look at this way, you just see that lambda tilde of P is indeed this unitary here. Now, if P and Q are very von Neumann equivalent, remember what that means is that there exists some V such that V star V is equal to P and V star is equal to Q, right? So if they are Murray von Neumann equivalent, then so are lambda tilde of P and lambda tilde of Q. Let me just add a proof here. Then lambda tilde of P is Murray von Neumann equivalent to lambda tilde of Q. Well, the first trick to observe here is that in matrix algebra, this here is equivalent to P and Q being unitarily equivalent. There exists U unitary such that UPU star is equal to Q. Why is that so? Well, basically, in matrix algebra, Murray von Neumann equivalent is for projections equivalent to having the same trace, and which is in turn equivalent to being unitarily equivalent. Okay, and now because our lambda is a group homomorphism, lambda of if we fix this unitary u, if you look at lambda of u times 1 minus 2p u star, this will be lambda of u star, and what we have in the middle, well, lambda of 1 minus 2p. So so basically what this shows is that right, okay, I forgot the first. This is really of lambda of 1 minus 2q. You see, if p and q are unitarily equivalent, then so are the corresponding unitaries. And because lambda is group homomorphism, this is being preserved. So Murray-Foreman equivalence projections is preserved by lambda. Next, if p and q commute, then so do lambda tilde of p and lambda of q. Now, why is that so? Well, p and q commute if and only if p plus q minus pq is is a projection or even is self-adjoint, which is maybe slightly more relevant here. Right, so p and q commute if and only if this is self-adjoint. And now what that means is that the corresponding one parameter groups associated to p and q also commute. And now lambda tilde sends them to, lambda sends commuting elements to commuting elements, and therefore lambda tilde has to pick commuting seeds for those one parameter groups. And now if p and q are orthogonal, then lambda tilde p, lambda tilde q is 0, and lambda tilde of p plus q is lambda tilde of p plus lambda tilde of q. Now again, this just translates into statements about these two unitaries, 1 minus 2p and 1 minus 2q. Yeah, so I don't, basically, PQ is 0. This is equivalent to saying that P plus Q is a projection. And again, by just looking at this unitary, 1 minus 2 times P plus Q, and seeing where lambda tilde sends it and unpacking everything, you get all this. Okay, and finally, if you have projections that add up to 1, so they are orthogonal, they add up to 1, then the same applies to their images. Now, this follows from 4 together with what? With the fact that lambda of 1 is equal to 1. Okay, and this is all we need to complete the theorem. So now remember, A has a faithful tracial state sigma. And all you need to prove is that if we compose sigma with lambda, we get tau, and now this is tracial state on MM of C. Now, and this has to be true for every unitary. Now, by the spectral theorem, we can write unitary as sum of basically, you just look at these rank 1 projections which correspond to eigenvectors. So you just diagonalize U, right? So diagonalize it. Now look at the eigenvectors. Pj is the span of the jth eigenvector. These x per I lambda j are the eigenvalues. I'm repeating eigenvalues with which have multiplicity more than 1, so that each one of these projections is a rank 1 projection. Now, okay, another thing is this sum is equal to the product. Note that Pj is under the exp sign here. And because these are all rank 1 projections, they're all Murray-Foreman equivalent. Now, what that means is that if I apply lambda to all of those, sum of lambda of pj's will be equal to 1. That was part 1 of the previous lambda tilde of pj's is 1. And also lambda of u will be, right, so because of this here, that's why I need this expression, because lambda is group homomorphism, lambda of u is product j less than m, lambda of exp I lambda j pj, and these are going to be orthogonal rank 1 projections, and eigenvalues are the same. So from there, you conclude that trace of u is exactly sigma of lambda of u, because it is just the sum of all these I lambda j's. I is square root of -1, not natural number. Right. So yeah, so I went a little bit over time, I guess, and I owe you this tick. But anyway, if you want to look it up, look up in the errata what is in the actual book is not entirely correct. Okay. So any questions? All right. So if not, thank you, and see you on Friday.